When we are writing a program, we must make sure that the program is efficient. That is, it must take the least amount of time to complete, and also it must consume the least memory space. Now, this time complexity and space complexity depends on only one thing: what the programmer writes in the code. So it's the sole responsibility of programmer to make sure that the program is efficient. Now, how do we measure the space and time consumed by the program? One way of doing it is by noting down the time and space consumed by the program by running it on the system. But when we run the same program on different systems, there can be differences in time and space consumed depending on the processor speed and the resource availability. Here comes the importance of asymptotic analysis and notations. Here, instead of taking the absolute values of the time and space consumed by the program, we will be using mathematical notations to represent the usage of time and memory space. We will take a graph in which the x-axis represents the input size and y-axis represents the time consumed or the space consumed. Here in this graph, we can represent the best case scenario, worst case scenario, and also the average case scenario of time or space consumed. We are more interested in worst case scenario because if we have taken care of the worst case scenario, then we need not have to be concerned about the best case or the average case. In asymptotic notation, the best case is called big omega, the average case is called big theta, and the worst case is called big O. We will be focusing on big O. Now let's take a program. The functionality of this program is to find the sum of first element and last element of the given input array. Now, since we can access the first element and the last element directly from the input array, we can always return the value at constant time. So this program runs at constant time and it is represented as big O of 1, and its graph looks like this. Now let's take another program. The functionality of this program is linear search. That is, we need to search for an element in the given array. Here in the worst case scenario, the element we are searching for can be at the end of the array. In that case, we will have to go through each n elements to reach the element we are searching for. So the program will be running at linear time. That is, it is represented as big O of n, and its graph looks like this. Now let's take another program. The functionality of this program is binary search. That is, in a sorted array, we need to find an element. Since the array is sorted, we can always find the element at the middle of the array. If it is not found there, then we will halve the input array into 2. And depending on the value of the element we are searching for, we will be either going towards the left side of the array or the right side of the array. Now what's happening here is, in each iteration, the size of the array is getting halved. In the first iteration, the size of the input array under consideration will be n. In the second iteration, the size of the input array under consideration will be n by 2. In the third iteration, it becomes n by 2 divided by 2. And for the kth iteration, where we will be finding the element we have been looking for, the size of the input array we'll be considering will be n divided by 2 divided by 2 divided by 2, that is divided by 2 k times. So we can simply write it as n divided by 2 raised to k. When we have finally found the element we have been looking for, we can say that the size of the array 1 equal to n divided by 2 raised to k, which implies n equal to 2 raised to k. Now taking log of base 2 on both sides, we get log n equal to log 2 raised to k, which can be written as log n equal to k log 2. So in the worst case scenario, the kth iteration is log n. So the time complexity is written as big O of log n, and its graph looks like this. Now let's take another program. The functionality of this program is to find all possible ways of selecting the fruits from the input array one after the other. That is, we need to find the permutation of selecting the fruits. If there are n fruits, then there will be n factorial ways of selecting the fruits. The big O time complexity of this program is big O of n factorial, and its graph looks like this. So similarly, based on what the programmer writes in the code, there can be different possible time complexities or space complexities like n log n, n raised to c, c raised to n, etc. If the program runs in the green area, we can say that the program is efficient. If it runs in the orange area, we can say that it's not that efficient but still acceptable. And if the program runs in the red area, we can say that the program is inefficient. Also, based on the application of the program, we can decide whether we need better time complexity or better space complexity. In most of the cases, it is not practical to attain efficiency in both time and space. So what developers used to do is attain efficiency in time complexity by sacrificing space complexity, or attaining efficiency in space complexity by sacrificing time complexity. Before I end this video, I would like to add 3 important points regarding this asymptotic notations. First point is, if there are multiple terms in a program, always keep the highest order term and ignore the rest. That is, we need to pick the worst among all. Second point is, if there is a constant multiplier with the input variable, we can ignore the constant because the input size decides the variation in complexity graph. And the third point is, if there is a constant added to the input variable, we can ignore that constant. Because when the input variable becomes large, that constant variable becomes very small or negligible. That's all. See you in the next video.